Now we'll see variation of G. First of all, we'll see the variation of G with altitude. So this is the first case, due to altitude. The variation of G, acceleration due to gravity due to altitude. For this, we will see here, we'll consider Earth to be a sphere of mass m, radius r, with center O. Let G be the value of acceleration due to gravity at point A. This is the point A, just touching the surface of the Earth, or you can say on the surface of the Earth. So gravity at this point on the surface of Earth can be given by G is equal to gm upon r square. The formula already we have derived this. G, that is acceleration due to gravity, is equal to capital G, universal gravitation constant, m, mass of Earth, upon r square, where r is the radius of Earth. Now we'll take this body little higher, like from the Earth's surface h distance. So if g dash be the acceleration at this point, B point, if g dash be the acceleration due to gravity at a point B, so at a height h above the surface of Earth, then the force on the body at B is due to Earth, whose mass is m, the small m here, the mass is m, is concentrated at the center O of Earth, that is the mass m, Earth whose mass is m, and concentrated at center O of Earth here. Then in that case, G dash is given by G dash equal to gm upon the square of the distance. Now you will see the square of the distance from the center of Earth is r plus h. So we'll take the square of r plus h. So this is r plus h. Now I'm just writing this as equation 1 and this is as equation 2. Now we'll see, we'll take the ratio of these two, equation 2 and equation 1. So just by taking ratio of equation 2 to equation 1. Equation 2 is g dash and equal to g dash equal to gm upon r plus h square, and equation 1 is g is equal to gm upon r square. Now we'll see, this is gm would be cancelled. It is g dash upon g. This is r square will go up here, that is r square, r plus h the whole square. Now we'll see g dash upon g, r square. From this r plus h the whole square, we'll take out r as a common factor. So this is r square, and in the first term it would be 1 only. Here r is not there, so we can write h upon r whole square. Now r square would be cancelled. G dash upon g is equal to 1 upon 1 plus h upon r square. So in that case we can write 1 plus h upon r square. If we'll take up it, then the exponent will become negative. That means 1 plus h upon r, and this is minus 2. Now if we take the case like if h is very small comparison to if you compare with radius of the Earth, that is r, and so that you can say simply the ratio of these two, that means h upon r is very less than 1. In such case, we'll apply here the binomial theorem. So by applying binomial theorem, we'll just take the two terms here and rest of the term we can cancel, as I explained you in mathematical tools. So g dash upon g is equal to 1. This is minus 2. This exponent will multiply with the second term, that is minus 2h upon r here, and rest of the term we can cancel out. That will give us the very small value, and that's why. So now you will see that the ratio of these two will be g dash upon g will be equal to 1 minus 2h upon r. Now we'll see g dash is equal to g 1 minus 2h upon r. We'll see here g reduced. Here you can see g reduce with increase of altitude, because this quantity, as I told you, this is less than 1. So if 1 minus something would be there, so in that case the quantity will come less and multiply with g, so g will reduce here. So we can say from this formula, that from this equation or the formula, you can say here g reduces with increase of altitude, with increase of altitude. We'll see here, this is g dash, multiply g with this term, so this is g minus 2gh upon r. Now you will see here g minus g dash, this is equal to 2gh upon r, or g minus g dash upon g is equal to 2h upon r. So this is called fractional decrease, that is fractional decrease in g is represented by this equation, where we can say simply del g upon g, that is g minus g dash upon g, and which is equal to 2h upon r. So if it is asked to you about the fractional decrease, you can write here the fractional decrease in the acceleration due to gravity with altitude is given by 2h upon r. Now if we talk about the percentage decrease, how much percentage will decrease? So percentage decrease can be represented by the equation just multiplying the fractional decrease with 100%. So this is g minus g dash upon g, that is here 100%, or you can say that is 2h upon r multiply with 100%. So this will give you the percentage decrease in acceleration due to gravity with altitude here. Now the next one is, we'll see, suppose we are writing the distance r plus h as small r. So in that situation, g dash is given by gm upon r plus h square is there, that formula we have derived. So this is gm upon r plus h square, or we can write this as a gm upon r square. From this formula you can, or this equation, from this equation you can see here g dash is directly proportional to 1 upon r square, or g dash is inversely proportional to the distance of square of the distance of the body from the center of the earth. So this can be, this variation of g dash with r can shown by the graph here. If you just draw the graph like this, so you will find, if we'll take g dash in y-axis and r in x-axis, so this will be exponentially decrease. G dash will decrease exponentially with increase of the altitude. Now we'll see a special case here in which, suppose the object is shifted to h distance, and that is equal to the radius of the earth, that is r equal to 6400 kilometer. In that situation, we'll see, as we have taken the ratio g dash upon g, that is equal to r square upon r plus h square. From this formula we can write here, that is g dash upon g, this is r square, and this r, in place of h we can write r here, square. So g dash upon g, this is r square and this is 2r square, and if you will take the square of this, 2r, the whole square, if you take the square of this will come 4r square. R square would be cancelled. Then g dash upon g is equal to 1 upon 4, or you can say g dash is equal to g upon 4. That means the acceleration due to gravity will remain 1/4 of the acceleration due to gravity on the surface of the earth, or you can say the acceleration due to gravity on the surface of earth is g, so g dash will be reduced by 25, g dash will remain till 25%. Now we'll see variation of g, acceleration due to gravity due to effect of depth or due to depth. For this, again we'll consider earth to be a homogeneous sphere of radius r and mass m with center O. Let g be the value of acceleration due to gravity at a point A on the surface of earth. Look at here, this is given here. This is earth and the mass of earth is m. The radius of earth is r. At point A, if any object of mass m is kept here, then in that case the acceleration due to gravity on the surface of earth is written here by this formula, g is equal to gm upon r square. Now if we'll consider here that because the earth is a homogeneous sphere we have considered, so the density of the material of the earth is, suppose, rho. So in that case it is, we'll see here, this is in that case the density if we consider rho, so the mass of earth, so the mass of earth we will write, because it is a sphere, it is 4 upon 3 pi r cube rho. That mass of earth is volume into density. The volume of earth is 4 upon 3 pi r cube rho. So we'll see here in this formula, if we'll put the value, the g is equal to capital G, universal gravitation constant, multiply with the mass is given by 4 upon 3 pi r cube rho here upon r square, then g will come here, the r square will be cancelled, it will come 4 upon 3 pi g r rho. So this is equation 1. That means the acceleration due to gravity at point A or on the surface of Earth is equal to 4 upon 3 pi g r rho. Okay, this is equation 1. Now we will see here for the suppose now the object is shifted to point B, that is depth d. So here in that case the acceleration due to gravity will consider g dash. So let g dash be the acceleration due to gravity at the point B, this point B, at a depth d. Look at here, this is at a depth d below the surface of the earth. From the surface of earth it is d depth below from the surface of earth. At point B that object is placed now. So the point B at a depth d below the surface of earth. Now the distance of the point B from the center of the earth, this is the center of the earth O. So from this point to B is now r minus d. This much distance will be less now. Okay, so r minus d will be the distance of this point B from the center of earth. Now the earth can be supposed to be made up of a smaller sphere. You can see this shaded part. As we know, the force that will work between this B and O, center of earth, for that this much mass of the earth will be responsible. That is the mass of this smaller sphere of the radius r minus d will be responsible. So the earth can be supposed to be made up of a smaller sphere of radius r minus d, and the body at B is inside the spherical shell of thickness d. You can consider the force on the body. Now this at B, the force on the body of mass m at B is due to a smaller sphere, due to this sphere of earth. Radius of this smaller sphere is r minus d, and is just as if the entire mass of this smaller sphere m dash of earth is concentrated at the center O. So in that situation we'll see here g dash. G dash, that means the acceleration due to gravity at point B, that is d depth from the surface of the earth. So g dash is now g m dash upon r minus d the whole square. G is the universal gravitation constant, and as I told you, m dash is the mass of this smaller sphere, which is responsible for the force between these two objects, earth and the object placed at point B, and the distance between them is r minus d. So square of the distance between them, that is r minus d square. And in this situation you will see that as we have taken out the density, because we have considered the earth as a homogeneous sphere, that means the uniform density would be there all over the earth. So in that case the density here also we will consider as rho, and now the mass m dash is given by volume into density. Now this time the volume is what? This time the volume is 4 upon 3 pi and the cube of the radius, but the radius is now r minus d. Okay, so this is the volume, 4 upon 3 pi r minus d cube the volume, and the density is rho. Okay, now so m dash is this. We'll place this value here in this equation. G, that is 4 upon 3 pi r minus d the whole cube rho upon r minus d square. This we call as equation 2. Now we'll take ratio of this equation 2 and 1, or we'll divide equation 2 by equation 1. So g dash is divided by g now. G dash is g 4 upon 3. This is, you can see here, I have not simplified it. R minus d and R minus d square will be cancelled. Only R minus d will be there. So g multiplied by 4 by 3 pi, only R minus d will be there, and this is density. Okay, because R minus d the whole square and R minus d the whole square, from here it will be cancelled. Only R minus d will be there in the numerator. So this is equation 1 and divided by equation, sorry, this is equation 2. The above one, the numerator part is the equation 2 and the denominator is the equation 1, which is g 4 by 3 pi r rho. Now we'll see that all this quantity g would be cancelled. 4 upon 3 would be cancelled, pi would be cancelled, rho would be cancelled. Now what is remaining here? The remaining value is, this is r minus d upon r. Now g dash upon g is equal to r minus d upon r, that r 1 minus d upon r. So this is the ratio of the acceleration due to gravity at point B to the acceleration due to gravity at point A. Now we will see here g dash is equal to g, this is 1 minus d upon r. This is 1 minus d upon r, and we can see that the depth of the till what depth the object can be taken. So from A to the center of earth the object can be placed. So this much depth would be there. So anyhow the depth will be not more than r. Anyhow the depth will be not more than r. That means the value d will be always less than r. The value d is always less than r except one position, when this object is placed at the center of the earth. So if d is less than r, that means the fraction d upon r is always less than 1, and if d upon r is always less than 1, then this quantity will be less than 1, and it is means whatever the quantity in the bracket will be the positive value, but it is lesser value. Then in such situation this g dash will be reduced. So once again we'll find that the value of acceleration due to gravity will reduce here. Okay, so again we can say the value of, this is the formula, this formula also we can use here. Okay, so the value of acceleration due to gravity decrease or reduce with depth. Now we'll see fractional decrease in the value of g due to depth. So for this, the formula which we have derived, that is g is equal to, g dash equal to g 1 minus d upon r. So we'll simplify it. G dash, this is g minus g d upon r, or we can say g minus g dash is gd upon r. This is g minus g dash upon g is d upon r. So the fractional decrease is, that is del g upon g, change in g or variation in g upon original g, that is d upon r. So fractional decrease is given by this formula with effect of depth, and we'll see the percentage decrease here. So for the percentage decrease, we can see, just multiply the fractional decrease with 100%. So we'll get the percentage decrease, that is del G upon G into 100%, or you can say D upon R into 100%. So this will be the fractional decrease here. Now one more thing that we can observe here, this is G dash is equal to G, that is R minus D upon R. R minus D upon R. This formula came. So this is G dash is directly proportional to R minus D. Now if you consider R minus D as R, that is R minus D as R. So in that situation, what we'll find as the value, this is directly proportional to R minus D. Okay. So the variation between the G dash and the D we can observe in this way by the graph here. Like as the depth increases, the value of G will reduce, and in the special case, when you just see the special case here, that is the special case, what it is, if the depth become this is depth D become R, that means from this figure you can understand better, that is the object B, object which is placed at B, and now when it is slowly come to the center, means by this way it come to the center. So what we have seen already, as the depth will increase, the acceleration due to gravity will decrease, and this depth can be up to maximum limit, that is R, the radius of the earth, and if it is D, it will become R. In such situation, the object will now come to the center. Okay, so here we'll see in a special case that if depth become D equal to R, or we can say the object placed at the center of the earth, placed at the center of the earth, that is O, at point O. So in this situation, we'll see from the formula, that is G dash equal to G 1 minus D upon R. So G dash equal to G 1 minus R upon R. Now G dash is equal to G 1 minus 1 minus 1, that will become 0. So G dash is 0. That means the value of acceleration due to gravity is 0 here. So we are looking towards the variation. In variation, what we'll see, if I'm just taking the G dash at y-axis and D at x-axis, so the value of G will decrease. The value of G will decrease up to 0. G will decrease up to 0. This way, as the D increases, G dash will decrease, the acceleration due to gravity will decrease, and when the D will become R, in such situation, G dash will be 0. In a special case, we have seen that if D is equal to R, that means if depth of the depth of the object where it is depth of the earth where the object is placed is equal to radius of the earth. That means the object is placed at the center. That means object is placed from the earth's surface, that is 6,400 kilometer distance at the center of earth. In that situation, g dash is equal to 0. That means acceleration due to gravity is 0 at the center of the earth, and therefore the weight of the body of mass m at the center of earth, that means mg is also equal to 0 because g is 0 here. But we know that the mass of the body will not be 0, and thus the value of acceleration due to gravity is maximum at the earth's surface, because both the cases we have seen already that when we are taking the object means far from the earth's surface or some height from the earth's surface or some depth from the earth's surface, both the cases we have seen the acceleration due to gravity will reduce. So this is the graph which you can observe and means understand very well. This is the whole graph explained to you about the variation between the acceleration due to gravity from the acceleration due to gravity and the distance from the center of earth. So you will see that at the center of the earth, that means when the object is placed at the center of the earth, g dash will be 0, and so that you will find that here this is 0, and from 0 to r, that means from center of earth to the earth surface, when you take the object, the acceleration due to gravity will increase here, and at the surface or on the surface of the earth, you can say the acceleration due to gravity will be maximum. Now if you take the object some height from the earth's surface, that is suppose 2r if you are taking, or 3r you are taking, or the 4r, that means just double of the radius of the earth or triple of the radius of the earth or 4 times of the radius of the earth, gradually you can see that the acceleration due to gravity will reduce, and it will be reduced exponentially from the earth's surface to some height, you can say 2r, 3r or 4r. Okay, so the maximum acceleration due to gravity is on the surface of the earth, and the acceleration due to gravity at the center of earth is 0. So this is the graph is explaining very well the acceleration, the variation between the acceleration due to gravity and the distance from the center of earth of the object. Okay, now you will see here one question: what is the relation between height h and depth d for the same change in g? We know that the acceleration due to gravity change when we'll take the object with some height, that we will explain here, we will just denote here with the letter gh, and the formula is given here. The variation will be equal to what? It is equal to g1 minus 2h upon r. Okay, and another formula we have seen for the depth, I am writing this as gd here, and this is equal to g1 minus d upon r. Okay, now according to question, it is given here what is the relation between height h and depth d for the same change in g. Same change in g, that means if similar change is there in the g, then gh is equal to, gh must be equal to gd. That means this is g1 minus 2h upon r must be equal to g1 minus d upon r. G would be cancelled. This is 1 minus 2h upon r, and this is 1 minus d upon r. Then 1 would be cancelled, minus would be cancelled, r would be cancelled, then remaining here 2h upon d. That means d is equal to 2h. The meaning is that if you take the object as d depth, or if you take the object up to twice the height, means 2h, okay, or the just equal to the depth of the object. So in that situation you will find the ratio of these two, that means d or d upon h. What you will find here, that is 2:1, 2:1. So in acceleration due to gravity you will find similar change when you take the object up to d depth or when you take the object up to 2h height. Now we'll see the third case, that is variation of acceleration due to gravity because of the effect of latitude or due to the rotation of earth about its own axis. Just to understand this topic, we'll see this figure first and we'll define latitude first. Latitude means what? Latitude at a place is defined as the angle which the line joining the place to the center of the earth makes with the equatorial plane. It is generally denoted by the letter lambda, and latitude at a place, look at here, this is the earth and we have this shaded part is the equatorial plane. From the equatorial plane, this point P on the earth's surface is making angle lambda here with this equatorial plane. So this is the latitude at a place at point P is called angle angle POE is equal to lambda. And you can see that if a place is located here on the means at the poles, that is whether north or the south, in such situation lambda will be 90, and at the equatorial plane, so then in case the lambda will be 0. Okay, so this is latitude. And now we'll see what effect would be there in the acceleration due to gravity due to the latitude and the rotation of the earth together. To understand this, in this figure you can observe here at point P we are considering a particle of mass m, small m. This is at place P of latitude lambda. That means it is making lambda angle with the equatorial plane, this location is. Now if earth is, this object is, okay, now if earth is rotating about its polar axis, that is north south, with constant angular speed or angular velocity omega, suppose this is in this way anti-clockwise direction, so omega is positive here. Now then particle at P also rotates. So this particle at P also rotates and describe a horizontal circle. In this circle you can see that this is the circle. In this object which is placed at point P also will be rotating. Okay, now at P also rotate and described a horizontal circle of radius r. This is the r, this one PC is r. Now where you can see this PC is r and this is a triangle PCO. Here you will find OP is capital R, that is the radius of the earth. So small r is represented as r cos theta, capital R, sorry, r cos lambda, because lambda angle is there. So if it is lambda, this will be also lambda because the alternate angles are here. So this will be lambda. So in such situation you will find the small r will be equal to, this small r will be equal to capital R cos lambda. This is equation 1. Okay, now what we can find here at this point P, the centrifugal force acting on the particle at P, and we know that the centripetal force is also working towards PC here, and the centripetal force which is working toward PC, that is mv square upon r, or you can write in the terms of the angular velocity, that is mr omega square. So a centrifugal force also work here at point P, and that will be working in this direction PA. This is the direction PA it is working. The magnitude of this force will be mr omega square. Okay, now it acts along PA directed away from the center C of the circle of rotation. Now suppose g, small g, is the acceleration when earth were at rest. मीन्स जब अर्थ रेस्ट में है उस टाइम पे acceleration due to gravity at point P is g. Okay, now what happen if because earth is rotating with the angular speed omega here, so in that case when earth then the gravity pull on the particle, that is true weight of the particle here, when it is in rest position, the true weight of the particle at point P will be working towards center, that is PO here. But when PO here, okay, that is x along PO, you can say. Now you will suppose here let g dash be the acceleration due to gravity at P when rotation of earth is taken into account. Then apparent weight also will be change of the particle, and that will be equal to mg dash, and this is the resultant of, this will be the resultant of the true weight and the centrifugal force acting on the particle at P, and hence must be represented by the diagonal PB here. You can see that this is PB. Actually when the earth is in rest position, in that situation the true weight of the particle at point P is towards center, and mg will work towards center of the earth here. Okay, now you will see that this is the centrifugal force, it is working along PA mr omega square due to the rotation of the earth. So the g dash, which is the apparent weight, means mg dash, which is the apparent weight of the particle, will be the resultant of this mg and mr omega square. We can make the parallelogram here with this just by taking this PA and PO as the two adjacent side of the parallelogram. Will complete this parallelogram. So where the diagonal will represent, that is PB is representing, that will be the direction of the apparent weight of the particle due to the rotation, or due to the latitude, you can say, due to the rotation of the earth. Okay, so that resultant can be given by the law of the parallelogram, and the resultant of the formula of the resultant of from the law of parallelogram is root of p square plus q square plus 2pq cos theta. It is the resultant is p square plus q square plus 2pq cos theta, where p and q are the two forces working here. So here the two forces are working is the mg, that is the true weight of the particle when the earth is in rest position, and q is the centrifugal force along PA, that is mr omega square. So the apparent weight will be the resultant of this. So mg dash must be resultant of the root of resultant of mg and mr omega square. If we put P as mg and q as mr omega square, this formula will write mg square plus mr omega square the whole square plus 2 mg mr omega square, and it is cos 180 minus lambda. You can see that the angle between these two forces, that is mr omega square and mg, that will be equal to 180 minus lambda, because it is lambda, so this will be also lambda, and this is a straight line that PC is representing the centripetal force. So PA will represent the centrifugal force. So the angle between these two forces will be 180 minus lambda. These are the linear pair. So if it is lambda, the remaining will be 180 minus lambda. So here we have written cos 180 minus lambda. Now we'll simplify it. We'll find that here m square will be there in all three terms. Then m square will come out from the root sign, that will be m. So here also m and here also m, both the m will be cancelled. Now remaining is what? That is g dash equal to g square plus m square r square omega to the power 4 minus 2g r omega square cos lambda. Because cos 180 minus lambda is minus 1, so here the plus sign will change into minus, and in place of root we have written the power 1 upon 2. Both are equal things. Okay, now g dash is equal to, we'll take common g here, so I have taken g from the this root sign, so square and half will be cancelled and g will be outside. Now here it will remain 1, here no g is there, so it will means g square will be divided, and in third term also the g square will be divided, but 1g is there in the numerator, so 1g upon g will be cancelled and that will remain g here. Okay, so you will find 1 plus m square r square omega 4 upon g square minus 2 r omega square cos lambda upon g. Now if you see the value of r omega square upon g, because all these quantities are known, that the radius of the earth, the angular speed of the earth, and the acceleration due to gravity of the earth, so you will find that this quantity is very small. And now if you take the higher terms of, means higher power of this quantity like a square or cube, in such situation that will be also very small. So therefore the higher power can be neglected, and in this equation we'll just apply the binomial theorem. So you will see that the higher term will be neglected, that means the second term will be neglected because it is the square of r omega upon g. Okay, so this term will be neglected. Remaining term will be what? 1 minus 2r omega square cos lambda upon g, and to the power 1 upon 2. Now if we'll apply binomial theorem, this power will be multiplied with the second term, that it will be multiply. So here the 2r omega square cos lambda and 1 upon 2 is multiply, so it will become 2g. 2 would be cancelled here, then g dash equal to g 1 minus r omega square cos lambda upon g. Okay, now we'll see that this g, if we'll take means this g will take inside, in that situation what you will find here, this will be cancel, that is g dash equal to g minus r omega, this g and g cancel, and r omega square cos lambda. Okay, now g dash is what? G dash is g minus, this is small r already we have seen from the equation 1. So from equation 1 we can write r is equal to r cos lambda, so this is r cos lambda omega square cos lambda. Cos lambda will be cos square lambda, so the formula came here, that is g dash equal to g minus r omega square cos square lambda. Okay, now what you will see here, r is a constant quantity, that is the radius of the earth. The variable quantity is omega square, that is the angular velocity of the earth. So angular velocity or angular speed of the earth, so angular is due to the angular speed of the earth, this quantity will change, that means g will change, and cos square lambda according to the latitude lambda will change, so the value of cos square lambda will also change, and so that you will find the change in the acceleration due to gravity. So what is there, the cos lambda is a positive value because it can vary from 0 to means it is vary from 0 to 90 degree here, that is from the equator to pole, so it will be positive always. And omega is, because it is in anti-clockwise direction, that is also positive, so you will find that this second term is positive. So if second term is reduced in g, means second term is subtracted by g, that means g dash must be less, that g dash must be reduced. Okay, so that therefore you will find that acceleration due to gravity decreases on account of rotation of earth, on account of rotation of earth. When the rotation will be high or the speed will be high, in such situation the acceleration due to gravity will reduce here, and it can increase with the increase in latitude of plane. How it is? For example, you can say that at equator lambda equal to 0, and if it is lambda is 0, that means the lambda is 0, that cos 0 is equal to 1, and it is the maximum value of cos. So when maximum value of cos is there, so this second term will be maximized, and so that the whole term will be minimized, because second term is subtracted from the first g, so the whole term will be minimized. Okay, so the whole term is minimum now, and that will be equal to g minus r omega square. That means at the equator, the value of acceleration due to gravity is minimum, and when we go to the pole or will increase to the pole, in that situation what you will find, the lambda is 90 degree and cos 90 is 0. That is the minimum value. If it is minimum, cos 0, which is the minimum value here, so because it is minimum, the second term will be minimum, so the whole term will be maximized. And now you will find g dash is equal to that is the gp, that is acceleration due to gravity at pole, and that will be equal to g only, because the second term will become 0 here, and this will be the maximum value. So what we find here, when we go from equator to pole, or when the latitude will increase, the acceleration due to gravity also will increase. When the angular speed of the earth will increase, the acceleration due to gravity will decrease, or the acceleration due to gravity at pole will remain unchanged whether earth is rest or earth is rotating. When earth is red, then also it is g, and earth is rotating due to the this latitude value, or because lambda is 90 degree, then also it will come g. Okay, so the acceleration due to gravity at pole will remain unchanged whether the earth is rest or rotating. Now we'll see the variation of acceleration of gravity with effect of shape of earth. We know that the earth is not a perfect sphere. It is flattened at the pole. You can see that it is flattened at the pole. That means what you will find here, the radius of the pole will be lesser than the radius of the equator, means equatorial plane. Okay, so the radius from the pole, if you measure it, that rp, and the radius of the equatorial plane, that is re, so rp is less than re. That means 1 upon rp is greater than 1 upon re. Now if you multiply here with gm, that gm upon rp, or you can take first squaring it. So when you are taking the squaring of this, 1 upon rp square will be more than 1 upon re square. So gm upon rp square will be more than gm upon re square. Gm upon rp square is gp, that is acceleration due to gravity at pole, and gm upon re square is the ge, that is acceleration due to gravity at equator. So acceleration due to gravity at pole will be greater than the acceleration due to gravity at equator. So the value of acceleration due to gravity increases as we go from equator to the pole, and because of the effect of shape of earth.